MV. It was 5.5 MV. Millivolt, right? Then
Yes, sir.
frequency F was 526, right?
Yes, sir.
526 hertz. So how you got frequency? From the time period, right?
Uh, yes, sir.
The time period was 1.9 millisecond, right?
Yes, sir.
The time period was 1.9 millisecond, and it was calculated from the time base, right? The
Yes, sir.
time base was given 0.50 millisecond per centimeter, and we calculated from the graph, the given graph. Hmm. From this trough to trough, the distance we are getting, that is 3.8 centimeter, right?
Yes, sir.
3.8 multiplied by 0.50 millisecond, we got 1.9 millisecond. Then we got
Yes, sir.
526 hertz.
Yes.
Now the actual uncertainty in F. Actual uncertainty is del F, right?
Yes,
Mhm.
sir.
Actual uncertainty is del F. So how will get del F? Any idea?
And no, sir.
No idea. So you know, this is from uncertainty. We got one idea like that. Del, if you want to get actual uncertainty, that is del F, right?
Yes, sir.
And you get one relationship, that is del F by uh, so you write here del F by F, huh?
Yes, sir.
Del F by F. We have this way del F by F equals, so del F by F you can find from the relationship we got for fractional uncertainty. Can you remember how we get it? We
Yes.
know that F equals 1 by T, right? This one we know, right?
Yes, sir.
So del F by F will be uh, del T by T, right?
Yes,
Isn't it?
sir. Yes.
So if it is del T by T, we write it del T by T. On the right side, we write del T by T. Ah, because we have only one quantity, that is T. That's why it will be only del T by T. T We have also
Yes.
like relationship. If we have more quantities, then we'll add them, right? Plus then another quantity we can add, right? This way we can do. So del t by t, we got here t we got 1.9 millisecond, right?
Yes, sir.
And how can we find del t? Del t we can find from here. Like when we got the uh, scaling here, right? 1 centimeter. You have your 1 centimeter, right?
Yes, sir.
So normally we get like in one ruler we have the smallest scale is 0.1 centimeter, right? That is 1
Yes, sir.
millimeter. So that one is the uncertainty in the reading, right? Similarly, here the smallest one is 1. Here we have 5 small square, so it is 0.2, right? Smallest square.
Yes, sir.
And if we are taking the average, that time we are having zero point 0.1 centimeter. So our uncertainty in reading of this smallest square, that is zero point 0.1 centimeter. Okay. So zero point 0.1 centimeter, this one is representing the time. We have the time based setting, that is 0.50 millisecond per centimeter, right? Isn't it?
Yes, sir.
So
Yes, sir.
if we want to get this zero point 0.1 centimeter in time, because we are having time period, right? Del t. So you have to convert it to time. It's zero point 0.1 centimeter. If we convert it to time, then it comes, del t comes, we are writing here, del t, you also write here side note, del t equals 0.1 centimeter times 0.50 millisecond per centimeter. Okay, so if you calculate
Okay, sir.
what is coming, check.
It comes 0.05.
So we write here 0.05 millisecond, right? Then we can put this value here. For del t it is 0.05, as you said, millisecond, Then for t time, we got previously how much? You said 1.9 millisecond, right?
Yes, sir.
So if you write it 1.9 millisecond, and if you simplify del t by t, what it comes?
Uh, what's
Is it like that?
It comes 0.03.
0.03? 0.026, right? Or
Yes, sir.
exactly 0 or exactly 0.03?
Yes, sir.
0.026. It's coming 0.026. Now this one is del f by f. That is fractional uncertainty. And actual uncertainty is del f, right? Isn't it?
Yes, sir.
So actual
Yes, sir.
uncertainty to get, we have to multiply this value with f. F we got 526, right? So we write here del f, actual uncertainty del f. We can do more working here. That is del f. We write here del f. Del f equals f into 0.05 millisecond. 0.026 here. 0.026 multiplied the frequency we got 526 hertz. So what is the answer here? Take
Uh,
0.026 multiplied 526, right?
yes, sir. The answer is 3.68. 13.68.
13.68, very good. So we can write here 13.68, right?
Yes, sir.
Or we can write 13.7, right?
Yes, sir.
13.7 hertz. So we got here actual uncertainty. Done.
Yes, sir.
This one, this part you can take the snap, this part only, and send it to our group.
Yes, sir.
Yeah, send to group. Okay, it's gone, right?
Yes, sir.
Now we have next question. This one you understood, right? The whole thing you understood, right? And
Yes, sir.
your previous learning and what explanation you got, does it match?
Yes, sir.
Okay, so no confusion. Now we are going to next part, last part, that is part B. State F with its actual uncertainty. That means you have to just write the answer. If you got 526, right? So if you write in two significant figures, you can write in two significant figures or three significant figures. Uh, you you write in two significant figures here. It is a standard value for both the
Yes, sir.
answers. I'm showing you why you prefer these two significant figures. Like if you write 526 526, then we write here 13 13.7. We got it right. So this one we can write excuse me. If we write in this way, then we have here decimal points, right? But
Yes, sir.
in uncertainty, is the norm or the practice that we have to write same decimal points. So if you want to make it decimal points, then you have here 526. Then after this you don't have anything. Then you have to write 526.0. Okay.
Yes, sir.
Otherwise you can write. Uh, so here you can write point 0. It will make it okay. Otherwise we can write 530, and here you can write 14.
14.
14, yeah, that one will match. This way it is a practice for writing the uncertainty, uh,
Yes.
the actual uncertainty with the measured value, that is frequency. So it's clear, right?
Yes, sir.
Now we are having question number 6 left, right? Only 6 is left, right?
Yes, sir.
From the structured part and from the whole worksheet, we have only question 6 left. So we try it now. So read it, please. Read the question.
Yes, sir. A source of radio wave sends a pulse towards a reflector. The pulse returns from the reflector and is detected at the same point as the source. The emitted and reflected pulses are recorded on a cathode ray oscilloscope as shown in figure 6.1.
Yes, read. Continue.
Yes, sir. Using figure 6.1, determine the distance between uh, the source and the reflector.
The time-based setting
And
is
the
given.
time-based setting is 0.2 microseconds per centimeter.
So it's the we know that echo, right? And the signal we are getting here, reflected one. So this pulse is showing us the uh, returning back sound, right? Isn't it?
Yes, sir.
Or returning back
Yes,
wave.
sir.
That one is showing. So they are saying we are sending pulse towards the reflector. The pulse returns from the reflector and is detected at the same point as the source. So it's the reflected pulse, this one. So from
Yes,
this
sir.
information, we have from this peak to this peak, the gap we have. That is 1, 2, 3, 4 centimeter, right?
Yes, sir.
So 1 centimeter is given 0.2 microsecond, right?
Yes, sir.
Then 4 centimeter will be how much?
Uh, it would be 0.8 microseconds.
So you write it that we have, this is time for reflected pulse, right? Returning back of the pulse this time. Then
Yes, sir.
the time to reach the reflector you can also find, right? Isn't it?
Yes, sir. Yes, sir.
And if you know, they are asking you determine the distance between the source and the reflector. So if the distance from the reflector and the source is d, then from the echo formula we can write v equals 2d by t, right?
Yes, sir.
Then we have d equals vt by 2, d equals vt by 2. Now already you got that t equals, we have here t is how much? 0.8 microsecond,
Uh,
right?
s- yes, sir.
0.8 microsecond. So v is our speed of radio wave in the uh, air, you know, right? Speed of the
Yes,
radio
sir.
wave. This is electromagnetic wave. So what is the speed? 3 into 10 to the power 8, right?
Yes, sir. স্যার আপনার কথাটা একটু আটকে আসতেছে স্যার।
Acha. So your speed of radio wave, electromagnetic wave in
Yes.
air, how much it is?
Uh,
3 into 10 to the power 8, right?
yes, sir. Speed of light.
Yes, electromagnetic wave, light, all are going with the same speed, right? In vacuum, in air.
Yes, sir.
So that value is 3 into 10 to the power 8. This one is radio wave. So radio wave is also one of the electromagnetic waves, right?
Yes, sir.
That's why it also has the same speed of light. So what is the speed? 3 into 10 to the power 8 meter per second. Then what is the time?
Yes, sir.
0.8.
0.8.
And then put these values 0.8 microsecond. Mind it, micro means 10 to the power minus 6, right?
Yes, sir.
So you have 10 to the power 8, you have 10 to the power minus 6. You can cut them, right?
Yes, sir.
And divided by 2, then what is the answer coming? Check. What is the answer coming? Check.
Yes, sir. I'm doing it.
Is it coming 120 meter? Check.
So my answer came 120.
Yeah, your answer came 120 and I also wrote 120, right?
Yes, sir.
So you got it right.
Yes, sir.
It's clear to you how to do. Then you have here, I'm
Yes.
writing the also steps how we did. Then V is speed of radio wave. This one. So you can also take the snap in the and send it to group.
Yes, sir.
Yeah, send it so that there is record. We can understand it later.
Yes.
So done. A part is done. Now we'll do B, part B. Okay, read part B.
Yes, sir. Determine the time-based setting required to produce the same separation of pulses on the mm, cathode ray oscilloscope when sound waves are used instead of radio waves. The speed of sound is 300 meter per second.
So time-based setting of radio wave we got right. That is
Yes,
0.20
sir.
microsecond per centimeter. Now for the radio wave, we also know the speed of radio wave, that is 3 into 10 to the power 8. Now we got the speed of sound, so we can get the ratio of speed of radio wave and speed of sound. But then if you do the ratio, what it comes? Hmm, if you do the ratio, what it comes? 10 to the power. This one is 300, right? So another one is
Sir.
3 into 10 to the power 8. So 3 into 10 to the power 8 divided by 300. What it comes? 10 to the power 6, right? 1 million.
Yes, sir.
So we can write sound is slower, right? Sound is slower by factor of 1 million, right? You
Yes,
write
sir.
10 to the power 6. It's easier for you to write 10 to the power 6 because here I have to sketch it if I want to write 10 to the power 6. That's why I wrote 1 million. Sound is slower by factor of 1 million than radio wave, right? So for radio wave, you got the time-based setting 0.2 microsecond, right? 0.2
Yes, sir.
microsecond per centimeter. Now, micro means 1 million, right?
Yes, sir.
So for sound wave, the time-based setting should be 0.2 second.
Yes, sir.
It will be 0.2 second because for sound it is taking more time, isn't it? like for each of the
सर अपने
centimeter,
contact cache this.
for light, we know light is faster, right?
Yes, sir.
And sound is slower. So
Yes, sir.
for radio wave we got 0.20 microsecond. That means 1 million. Time is very small to reach 1 centimeter, isn't it?
Yes, sir.
But for sound, it's taking more time. That's why time-based setting will be greater in sound wave, and that one should be uh, greater. How much greater? 1 million time greater. So 1 million and 1 million cut. It comes now 0.2 second per centimeter. So
Yes, sir.
time-based setting. So time-based setting, like uh, setting for sound will be 0.2 second per centimeter. Okay.
Yes, sir.
Have you shown the factor? You have to show the working here for that one mark, like 3 into 10 to the power 8 divided by 300. This one you show the working, eh? Is it
Yes,
clear?
sir.
That one is coming 1 million. That is 10 to the power 6. That one you have to show. For that one mark
Yes, sir.
for showing the calculation. So our this worksheet is over. This worksheet is
Yes, sir.
over. You please take the printout and write this all things in your worksheet. That will be a very good note for you for taking AS preparation. Okay.
Yes, sir.
So you join after 7 minutes. Eh? It's now 8:20. 8:27 you join again. Okay. We will
All
start
right, sir.
new. We will 8:27 you will join. We will start new topic. Okay. Topic
All
3.
right, sir. All right.